So in the previous video, I talked about collagen fibers, tendons, ligaments, which are collagen fibers. And now we're going to talk about articular cartilage, which are, in a sense, again, contain collagen fibers. Articular cartilage are usually found in the surface of a bone, especially the long bones, the ends of the long bones, and they allow for almost frictionless transfer of force or load, with bendings allowed and shears allowed. So here we have a diagram of an articular cartilage. This is the layers of articular cartilage. So if you would take the cartilage and slice it, this is what you'd see. At the top, the superficial layer, there are collagen fibers parallel to the surface. It doesn't necessarily have to be right to left. If this was another slice, it can be like up and down, if this was the image. But the point is, it's parallel to the surface. And this is important because this is what reduces the friction. Because if you have another articular surface on top, what's going to happen is it's going to allow sliding between the two. Whereas if this was sticking out, if the articular cartilage were like in this form, what's going to happen is that it's going to cause a rough area to form, and so allowing for more friction to be produced. So you can see that being parallel is really important. And then the middle layer, it's going to be a little more random. This is kind of like the absorbing layer. Absorbs the energy, kind of absorbs the energy that's coming in, kind of like a spongy thing. And then we have the deep layer, which is now perpendicular to the surface. And the reason for this is to allow, like columns, vertical columns, to absorb that energy once it travels all the way through here, to just stop it and resist it almost again. This is called the deep layer. And then right under that will be the calcified region. Calcified cartilage is the calcified region of the articular cartilage. And it allows it to connect to the bone, which is calcium hydroxide and calcium phosphate. So it allows it to connect to that. So we can see here there's cortical bone, and below is a spongy bone. This is not to scale, but like the idea should be there. Okay, so now let's look at now strain response to these articular cartilages. If this is a stress, if we call this stress, then the strain versus time would look something like this. Initially, strain would be 0, and then it will slowly start giving in. It will slowly start giving in. Eventually, at infinity, it's going to reach that point where it's going to slowly change its shape. It's like if you have a very thick Play-Doh, and that's not that a good example, but like if you press on it, and then press it with a constant force, it's going to slowly give into the shape you leave it in. Okay, so how do we imagine what's happening? So what's happening over here is that when you suddenly apply a force, and assume this is a cartilage, and this force is only in one direction. Initially applying the force, and there are cartilage fibers over there. What's going to happen is that now the collagen fibers are resisting that force initially. But because of that force, this collagen fibers will rearrange themselves. Notice they're going to be a little more flatter. By changing their shape a little bit, they're going to allow more deformation to occur. And then as time goes on, it will allow to finally reach a final strain. And I skipped this part, but yeah, here, this is a copious fluid exudation. What's happening here, as I said, even though they're being realigned, what's also happening is that liquid now is being removed from places and redistributed, because initially when you apply the force, the top part would have a very high pressure, and that's what's going to resist the force. But eventually, when that excess fluid in that area will seep down through and distribute itself out, it can reach this initial first state, and then eventually, after it's going to start using the known as the creep phenomenon, is going to just relax at that position. And then it's going to stay there once it's that position. Okay, we have another one, but now, what if we keep strain constant? And what if we keep strain constant and then see the stress? If this is strain, what if we keep strain constant and see the stress? So now let's break up into points and see what happens. Initially, we're at stress 0, and we start to apply a force. We start to apply stress. My bad. we try to apply a strain. So we're constantly increasing the strain, and you see there's this kind of response, a little more, like parabolic-ish. It's going to go on, and then it's going to slowly start rising up until we stop at the maximum strain. So we're here, this is A, and then we're B, we're going to strain it to this much. We're keeping the strain constant. Well, then what's going to happen? Through this point, what's going to happen right at this point, there will be a lot of force being experienced, and so because it's a viscous, it's not like a liquid that can just suddenly just transfer down. Because it's viscous, it's going to slowly take time. It's going to take time to slowly drift down and distribute its force evenly. So what's going to happen is at this point, it's going to have its highest stress. The internal stress in here will be the highest. And then what's going to happen is, once we lock it down, this is I made a mistake. This is going to be A, and this is going to be B, and this is C, and this is D, and then we need an E. No, my bad. Sorry, there's a little mistake here. Let me just quickly fix it up. Yeah. A is going to be the initial point. B would be this point. C would be this point. D would be this point, and then E would occur over here. Let me just let you know that. So initially, we're going to have a position. We apply the force here. We're going to have a strain here at this position. At this position, we have a stress over here. And then once we reach our maximum strain, after B, after point B, the strain is not going to change. That's why you can see over here, the strain is not changing. This length will always be the same. We're not gonna squish it over here. If you've seen this example, we're not gonna let this disc allow it to go down anymore. We're just gonna lock it there. Once it's locked at that position, what's gonna happen is that now the fluid at the top layer would slowly drift down. Eventually, when it distributes evenly, there's no more such high pressure being produced at the top. So then that means it can relax a little bit. The top part doesn't have to apply too much force onto the piston if it's a cylinder. And in other words, the stress at this point wouldn't have to be that high, because then that will be distributed evenly. So this stress at this point being supplied to the piston will be a lot less, because it has already been distributed at infinity.